James Webb Space Telescope is changing our understanding of the universe. The James Webb Space Telescope, JWST, is making scientists rethink what we know about the beginning of the universe. It's like we need to rewrite the textbooks. As astronomers try to understand the first stars and galaxies that lit up the cosmos, they're making amazing discoveries, thanks to JWST, also known as the $10 billion time machine. JWST is designed to see the faint infrared light from the universe's earliest objects. It looks back into the first few 100 million years after the Big Bang, giving us the best data we've ever had about newborn galaxies. In just its first year of observations, it has found more early galaxies than scientists ever expected. This has left researchers both excited and puzzled. Charlotte Mason, an astrophysicist, mentioned that they weren't expecting to find so many galaxies this early in the universe's history. After JWST's discoveries, scientists hurried to explain what they were seeing. Were these galaxies real? If so, how do they fit into our existing models of the universe? Or are these discoveries showing us that the universe is stranger and more complex than we thought? To understand the dilemma, let's go back to the beginning. After the Big Bang, the universe cooled down, and atoms began to form from electrons, protons, and neutrons. This quiet and dark period is known as the cosmic dark ages. Then, dark matter, which we can't see but makes up most of the universe, started to clump together. These clumps attracted atoms, forming the first stars and galaxies, which eventually led to the complex web of galaxies we see today. In the 1920s, astronomer Edwin Hubble discovered that the universe is expanding. The Hubble Space Telescope, launched in the 1990s, found that this expansion is accelerating. Imagine the universe as a loaf of raisin bread. As the loaf rises, the raisins, galaxies, move further apart. This accelerated expansion is driven by dark energy, a mysterious force. To test our understanding of the universe, astronomers look at distant galaxies. The further away they are, the older they are, letting us see back in time. In 1995, the Hubble Space Telescope captured thousands of galaxies in a tiny patch of space, revealing much more than anyone expected. The most distant galaxy it found, GN-Z11, existed about 400 million years after the Big Bang. JWST was built to see even further back in time. It has already found galaxies incredibly close to the dawn of time, much sooner than our models predicted. This suggests that galaxies grew big very quickly in the early universe. Chris Lovell, an astrophysicist, said we don't expect to see such massive galaxies so early because there hasn't been enough time for them to form. However, some of these early findings are being re-evaluated. Some galaxies initially thought to be very old are now believed to be younger due to better data and telescope calibrations. For example, a galaxy called Sears 1749 might actually be part of a cluster that's 12.4 billion years old, not 13.7 billion as first thought. To confirm these distances, JWST uses spectroscopy, which is more precise than just measuring brightness. It's like using a DNA test instead of just looking at someone's face. Combining both methods has given more accurate ages for some galaxies, but there's still much to learn. When a galaxy's light appears to drop off at longer wavelengths, it means the galaxy is more distant. The James Webb Space Telescope, JWST, has allowed researchers to identify spectra with redshifts up to 13.2. This redshift indicates that the light from these galaxies was emitted 13.2 billion years ago, almost at the beginning of the universe. As soon as this data was received, the researchers began to celebrate in their shared Slack group. Kevin Hain, an astronomer at the University of Arizona, shared that the group was ecstatic, repeatedly saying, oh my God, we did it, we did it." These early results are just the beginning of what could be groundbreaking discoveries in astronomy. Brant Robertson, another astronomer working with the JADES team at the University of California, Santa Cruz, explained that the early universe changed rapidly in its first billion years. During this period, galaxies evolved 10 times faster than they do today. He likened this rapid evolution to a hummingbird, a small creature with a heart that beats so quickly, it lives a different life compared to other creatures. Similarly, these early galaxies had a much faster heartbeat than the Milky Way, evolving at a pace we previously didn't understand. However, this rapid evolution raised a question: were these galaxies evolving too fast for the CDM, lambda cold dark matter, model to explain? As the public marveled at the new images from the JWST, researchers worked tirelessly to determine if these early galaxies fit into the existing CDM model or if new parameters needed to be introduced. One crucial aspect they examined was the masses of the earliest galaxies. Cosmologists try to determine a galaxy's mass from its brightness, but Megan Donoghue, an astrophysicist at Michigan State University, noted that this relationship is based on educated guesses. These guesses rely on assumptions derived from known stars and well-studied galaxies. One key assumption is that stars always form within a certain statistical range of masses, known as the initial mass function, IMF. This IMF is essential for determining a galaxy's mass from its brightness because hot, blue, heavy stars produce more light, while most of a galaxy's mass is usually in cooler, red, small stars. However, if the IMF was different in the early universe, these early galaxies might not be as massive as their brightness suggests. This potential difference poses a challenge because altering this fundamental parameter in the CDM model could yield vastly different results. Some astronomers even consider adjusting the IMF as entering the domain of the wicked. Wendy Freeman, an astrophysicist at the University of Chicago, mentioned that if we don't understand the IMF, understanding galaxies at high redshifts becomes extremely difficult. Her team is working on observations and simulations to better determine the IMF in various environments. As the months passed, many experts began to suspect that adjustments to the IMF and other factors might be sufficient to reconcile the ancient galaxies observed by JWST with the CDM model. Rachel Somerville, an astrophysicist at the Flatiron Institute, believes it is likely that these observations can fit within the standard paradigm. She explained that the findings teach us how fast dark matter halos collect gas, how quickly the gas cools and becomes dense enough to form stars, and how these processes might have occurred more rapidly in the early universe. There is also a possibility that black holes played a significant role in the early universe. Some astronomers have discovered a few glowing supermassive black holes at a redshift of 6 or 7, which is about 1 billion years after the Big Bang. It is challenging to understand how stars could have formed, died, and collapsed into black holes that quickly. If black holes were present inside these early galaxies, they could explain why these galaxies seem so bright even if they are not very massive. Somerville suggested that black holes could be causing these galaxies to appear brighter, making them look more massive than they are. Confirmation that the CDM model can accommodate some of JWST's early galaxies came just before Christmas. Astronomers led by Benjamin Keller at the University of Memphis reviewed several major supercomputer simulations of CDM universes. They found that these simulations could produce galaxies as heavy as those spectroscopically studied by the JADES team. These galaxies, however, were smaller and dimmer than other early galaxies such as Glass Z12. The simulation showed that galaxies of the size found by the JADES team could exist at a redshift of 10, and one simulation even created galaxies at a redshift of 13, matching JADES observations. These results indicated that none of the galaxies observed by JADES team fundamentally challenged the CDM model. However, these early galaxies have unique characteristics. Kevin Heinlein pointed out that the stars in these galaxies appear unpolluted by metals from previously exploded stars. This suggests they could be population 3 stars, the first generation of stars to ever form. If true, this means JWST has already glimpsed back to a time when the universe was first set on its current course. Despite these profound findings, the early universe appeared unexpectedly bright and massive. Leah, who co-authored a recent paper, said that some of these early galaxies are as massive or even larger than the Milky Way, which is astonishing given their age. One galaxy might have a mass 100 billion times that of the Sun, comparable to our Milky Way, which had 13 billion years to grow to its current size. Erica Nelson, an assistant professor of astrophysics at CU Boulder, called these findings universe breakers because they seem to defy our understanding of how quickly galaxies could form. For a brief moment, these discoveries seem to challenge the fundamental understanding of the cosmos. However, recent computer simulations guided by the standard cosmological model show that the universe could indeed have created some of the galaxies discovered by JWST. While the data initially seemed inconsistent with cosmological models, it is likely that our understanding of galaxy formation needs to evolve. There are many possible explanations for why early galaxies formed so quickly. One theory is that early stars formed more efficiently through mechanisms scientists have not yet considered. Alison Kirkpatrick, an astronomer at the University of Kansas, wonders if cosmic dust in these galaxies could be tricking JWST, making stars appear older than they actually are. Additionally, cosmic dust might have had different properties back then. Evo Lab, an astronomer at Swinburne University of Technology, suspects that black holes could be contributing to the brightness of these early galaxies, making them appear more star-filled than they are. Regardless of the exact cause, the first galaxies are not what we expected. Even accounting for potential new phenomena, everything appears too massive and too developed too soon. Investigating these questions will require more JWST observations, especially detailed measurements of starlight known as spectroscopy. Researchers need this data to confirm if the most unusual galaxies they have found are real and as old and massive as they seem. Understanding their composition will help astronomers understand the conditions in which they formed. Full spectroscopic data is expected to come in this spring, and it might take up to 5 years before we fully understand the new universe revealed by JWST. Ren Hsues, an astronomer at UC Santa Cruz and Stanford, believes it will take time to settle into our new understanding. JWST's first year focused heavily on hunting for the earliest known galaxies, formed just a few 100 million years after the Big Bang. This focus will continue in Cycle 2. Daniel Eisenstein from Harvard University hopes to push JWST to its limits by searching for galaxies up to 200 million years after the Big Bang, looking for those with redshifts beyond 15. Rohan Naidu from MIT, along with Jarrett Matthew from ETH Zurich, will use a giant cluster of galaxies to magnify the light of smaller objects up to 750 million years after the Big Bang, searching for clusters of population 3 stars. Closer to home, Christopher Glein from the Southwest Research Institute will use JWST to study Saturn's moon Enceladus, which might have a habitable ocean beneath its icy surface. Observations from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, showed that Enceladus occasionally ejects water from its ocean via a plume at its south pole. JWST will look for evidence of ocean chemistry on Enceladus's surface, including ammonia and organic molecules that could indicate habitability. Not all research areas were successful in securing time on JWST. David Kipping from Columbia University submitted 2 proposals to hunt for moons orbiting exoplanets, known as exomoons. He believes JWST is capable of finding these moons, but both proposals were rejected. Kipping is determined to keep trying, as JWST is the only telescope currently capable of making such discoveries. Despite the disappointments, those who secured time on JWST are thrilled about the scientific opportunities ahead. Nancy Levinson, interim director of the STSCI, emphasized that there is a range of exciting science that JWST is perfect for, and we are just getting started. The coming year promises to be filled with more groundbreaking discoveries as astronomers continue to explore the universe with JWST. That's all for today. If you enjoyed this segment, please leave a comment, give us a thumbs up, and we'll see you next time.